Well, hello everybody, and welcome to the first video for part 3, where we're going to look at a different model for light, the so-called photon model of light. So in part 2 and in part 1, we had the idea of the electromagnetic wave. Now we're going to see that there's an alternate model to light that's really a complementary model. So the photon model, which some people call a particle model of light. So we'll see that there are some physical phenomena that we can explain using the wave model of light, but others are going to require us to use the photon model. So that gives rise to what's sometimes referred to as the wave-particle duality of light. And we'll say more about that later. But to start things off, in this video, we're going to look at thermal radiation. This is sort of the starting point for the idea of the photon model. And what I'm looking at right now are the summary notes for part 3. So this is the first topic, thermal radiation and photons. So let's talk a little bit about thermal radiation, and I'll keep coming back to this summary, the summary notes here for important formulas. But the idea is, and this is somewhat historical, the way we're going to look at these things, the way the photon model was developed. So this phenomenon, people knew about thermal radiation. In fact, they were doing experiments with thermal radiation. They were measuring the spectrum of thermal radiation. But what we mean by the thermal radiation is that all objects, and I'm just going to make a generic object like a cube. So if we have a cube right here, oops, I do this all the time. I forget to turn my pad on. So I'm drawing over here and nothing's showing up. Oops, there we go. That was from our other previous discussion of the grading. Let me scroll down. Okay, here we go. So I'm going to draw a cube right here. Okay, so this is just some object, generic object. And its surface is at some temperature T. Well, we know, and people observe this, that this will give off electromagnetic radiation in all directions. This is so-called thermal radiation, and it's coming from the motion of the charges of the atoms and molecules on the surface and right below the surface. So this thermal radiation does have a dependence on temperature. If you look at the spectrum, all the different frequencies. So one of the things people would do is they would collect the light, the thermal radiation, put it through one of these spectrometers to break it into different frequencies, right? So what does that spectrum look like? Okay, well, if I go to the summary notes, I have a picture here, and I know that it's pretty low quality resolution, right? It's hard to read. So what I'm going to do is, let me show you. I want to point this out right now. If you go to our course page, which is right here, let me move this over. Where I am, let me back out. I'm on our web course page. See right here where it says test study questions? Well, that's a PDF of questions you should know. If I go to the online format right below there, these are the same questions of things you should know. But if you go to test 2, there are what I call quantum physics study questions that you should know the answers to, in addition to the typical quantitative type things like formula stuff. Okay, so there is some just information that I want you to know. And those quantum physics study questions are listed right here, and they'll appear in the PDF. But here's the link that I want to point out. If you click this, you'll get a PowerPoint presentation, which is what I'm looking at here. I've blown it up so I can see the plot. But this PowerPoint presentation will ask you those quantum physics study questions, and then the answers will appear. And if you do this in animated screen presentation mode, you can get the question without seeing the answer. Okay, so this PowerPoint here, this quantum physics study questions PowerPoint that you can find in the study questions for test 2, it might be a nice tool to review those quantum physics study questions. And I'll keep referring to it, showing you this in the video. I'll keep using some of these slides. But this is what I want to do now, is use one of these slides, because right here, let me scroll up. If you look at the red, the green, and the blue, those are experimentally measured thermal emission spectra. So you can see on the left, this is just arbitrary intensity. And then on the horizontal here, you have the wavelength in nanometers. Okay, now these 300K, 400K, 500K, those are the surface temperatures of the object. All right, which I know those are rather hot, but to get a lot of thermally emitted light in the visible portion of the spectrum, which is going to be right around here, right around 500 to like 700, 400, 700 nanometers, the surface has to be pretty darn hot. Okay, but I want you to just see the general profile. Do you see that profile? So at the lowest temperature, you get this peak, right, in that red curve, then it goes down. For the green, right, that's 4,000 K, so the surface is hotter. You'll notice that you get more intensity. The intensity, think of the area underneath the curves. So there's more total intensity, but also notice the peak of the curve shifts to a shorter wavelength. See, the peak of the 3,000 K is out here, maybe near between 900 and 1,000 nanometers. 4,000 K, that peak has shifted down to maybe 750 nanometers. 5,000 K, that peak has shifted down even more in wavelength. Okay, so people were able to measure these spectra as a function of temperature. And by playing around with these observations, they were able to actually write down some empirical relations. In fact, if you look at the peak wavelengths of the emissions, you can relate the peak wavelength and the surface temperature. And if I'm going to go back to the summary notes, that's what you see right here. This is known as Wiens Displacement Law. So the maximum wavelength, and that's maybe not written as well as it could be. What I mean by lambda max is not the longest wavelength, but the maximum intensity. This is the peak wavelength, the peak of the intensity. It's equal to 0.0029 meter times Kelvin over the temperature. Okay, so that's known as Wiens Displacement Law. You should know how to use that. Now realize we are going to be using Kelvin for our temperature scale. So I remind you guys up here are temperature conversions, right? So Celsius plus 273.15 will get you Kelvin. And then you can convert Celsius to Fahrenheit or vice versa using this equation right here. So just don't forget your temperature conversions. Write them down on your study sheet when you come to take a test, and you can use them for homework too. So here's Wiens Displacement Law. Interesting, empirically derived. You can also, if you look at the curve, and I'll just refer to these spectra since we don't need high resolution. If you look at the area underneath these curves, again, that's going to tell you about the total intensity. Intensity is power per area, so you can get information about the total power emitted in the thermal radiation by looking at the area underneath that curve. And you can get another empirical law, which is right here. This is now known as Stefan's law. The total power emitted in the radiation, the thermal radiation, is equal to, and we'll describe these things in just a second, this epsilon sigma A T to the 4. Okay, so you should know that also. All right, so what's this epsilon, the sigma, the A, and the T? Okay, so come down here. The epsilon is something called the emissivity of the object's surface. And it's really like a fudge factor, if you will, because each surface, right, what's giving rise to the thermal radiation is the motion of the charges on the atoms and molecules. So certain surfaces, that motion is easier, if you will, or different than other types of surfaces. So we put that through this number, which is between 0 and 1. It's called the emissivity. Okay? Sigma is just a constant. We call it the Stefan-Boltzmann constant. Its value is right there in SI units, 5.67 times 10 to the minus 8 watts over meter squared times Kelvin to the 4. The A is the surface area of the object. So if I'm looking at the cube, it's the surface area of that cube. That's going to be in square meters, SI units. T, as you would guess, is the temperature of the surface of the object in Kelvin. Okay? So we have that. Now, I'm going to throw in here something else so we can just talk a little bit about thermodynamics today. If you look at the power absorbed from the surroundings, so let me go back to my notebook. So this cube is sitting in some surroundings. I'll just sketch, like it's in some box, if you will, or in some room. And let's assume that the surroundings, the surface of the surroundings, they are at some average temperature, right? We'll call that T sub SUR. So the surroundings, right, it is emitting its own thermal radiation, right? And that radiation, some of that radiation is going to hit the object. So the object is absorbing thermal radiation as it is emitting thermal radiation, right? There's this process that's ensuing where it's emitting thermal radiation and absorbing thermal radiation from the surroundings. If you look at the rate that the energy is absorbed, that's the absorbed power, you can write down this law that you see right here. The absorbed power, so the power absorbed by the cube in our case, is equal to the emissivity of the cube surface times the constant sigma times the surface area of the object, the cube in this case, but times the temperature of the surroundings to the fourth power. Okay? So the A and the epsilon, that's the area and the emissivity of the object that we're also looking at emitting in the above equation, right? But the rate that that object is absorbing the energy is proportional to the temperature of the surroundings to the fourth power. Okay? So again, that doesn't have anything to do with the thermal radiation. Well, I shouldn't say that. It's not the thermal radiation that's being emitted by the object. This is the thermal radiation from the surroundings that's being absorbed by the object. Okay? Now, a little bit of thermodynamics. It turns out that what we mean by thermal equilibrium, radiative thermal equilibrium, and you don't have to remember this is just bonus, but radiative thermal equilibrium for that object and the surroundings means that the rate of emission of power equals the rate of absorption of power. So the P emit and the P absorb would be equal for this object. That we would say means that the object is in thermal equilibrium with its surroundings. Well, if you equate these two equations, what you conclude is that the temperature, the surface temperature of the object is equal to the temperature of the surroundings, right? So a lot of times when you ask people, hey, what does it mean if that cube is in thermal equilibrium with its surroundings? They might say, oh, the temperatures of the two are the same. That's correct, but that's because the definition of thermal equilibrium is that the emitted power equals the absorbed power, and it so happens that those powers are proportional to the temperature of the object to the fourth power for the emitted and the temperature of the surroundings to the fourth power for the absorbed power. Okay, so anyway, I thought I'd throw that out there. Another thing that you don't have to remember, but I'll just throw out there is what we mean by the term black body and white body in thermal physics. So a black body is something that absorbs thermal radiation really well. Okay, really, really, really well. So if you think about it, let's suppose I have an object, right? I'm not talking about emitting right now. We have an object, and you hit it with white light. If this is a really good absorber, it'll absorb every frequency in the white light. So what color is it going to look to you, right, in reflected light? Well, you're not getting any reflected light, so it'll appear black. So if that's the case, if I have a really good absorber, if I look at this equation down here, that means the emissivity is 1. That's what we mean by an ideal black body. The emissivity is 1. Well, if the emissivity is 1, then, if you look up here, that means this thing is a really good emitter of its own thermal radiation. Okay? So, an ideal black body is a so-called perfect absorber of incoming radiation, but it's also a perfect emitter of its own thermal radiation. So it can be a little confusing, that term. You contrast that, and an example of a black body. Often if you look up, what's a good approximation? What could be approximated well as a black body, an ideal black body? You might find a piece of charcoal, like regular old, charcoal briquette, which is true. That's a pretty good approximation because it definitely looks black, right? When you look at it in reflected light. And it's also a good thermal emitter. But, and this may be counterintuitive, a star is also a really good black body. Right now, a star is very, very bright, but that's because it's so hot. Remember, really good black bodies are really good thermal emitters. So because it's so hot, it's just going to be giving off all sorts of visible light in particular. But it's also a great absorber. Any electromagnetic radiation from other sources, other stars, right, or reflected light from planets, that electromagnetic radiation is going to be absorbed really well by the star if it makes, crosses the star's path. Okay, anyway, a little bonus material there. All right, so let's get back to what we're going to talk about here. Historically, right, people were able to get these thermal radiation spectra, and they were able to formulate these equations right here, okay, empirically. So then, and there's a lot of talking here in this video, not too many formulas, right? But I promise I'll try not to blab too much. But what people then did is they said, okay, look, and this is at the time that the wave theory of light now has been developed, okay? And people are like, hey, I think this is right. I'm sorry, Newton, but your corpuscle theory, it's going to be replaced now by this wave theory of light. So people said, well, let's look at other optical phenomena, right, that we've had a hard time explaining things from theory, and let's try this new wave model. So this was one of the first phenomena that people tried to derive theoretically using the wave model of light. Specifically, two guys, Rayleigh and Jeans, they wanted to see if they could theoretically get these emission spectra. Could they actually predict this curve theoretically? Now, what they did, and again, if you forget all this, it is just fine, but it's interesting information. Oh, actually, don't forget all of this, because some of this you're responsible for in those quantum physics study questions. So what they did is they said, all right, what we're going to consider is, if we look at this object, right, we're going to consider these charges, and on the surface, right, these charges, they're oscillating with some frequency f. Now, there's a whole bunch of different frequencies, okay, a whole bunch of different frequencies. But if you look at one guy that's oscillating at one particular frequency, I'll just draw it over here so it's not cluttered, this will give off electromagnetic radiation at that same frequency. I mean, that's predicted if you have an oscillating charge with this wave theory of light. So you can imagine then on this surface, you have a whole bunch of these charges all oscillating at different frequencies, so we should be getting thermal radiation at all different frequencies and wavelengths. And for sure, the spectra, they are continuous, right? If I go back to the spectra, you can see I'm getting all wavelengths here, okay? So that makes sense. But what they did is they said, okay, now this is a lot of charges to keep track of, so we're going to use some statistics. Now at the time, And what they need is really an energy distribution. If you guys have any probability or stats, you've talked about probability distributions. So what they did is they went to a distribution that had been used very successfully. It's an energy distribution, the Boltzmann distribution, and it's a distribution of energy. And where Boltzmann was able to use it successfully is in deriving the ideal gas law. He said, look, if I have this box of particles all moving with different kinetic energies, right? I need to say something about the probability distribution of those energies. What's the probability that a particle has an energy between this value and this value? So he developed this Boltzmann distribution, and using it was able to theoretically derive PV equals nRT. It's a cool derivation. We're not going to do it, but it's cool. So Rayleigh and Jeans said, well, we have a similar thing going on here, right? Because all these different frequencies, those correspond to different energies. So maybe what we can do is use this same energy distribution. And I mean, again, you don't have to know this for sure, but it turns out that this energy distribution is proportional to E, that's, the exponent, the natural log exponential, to the minus energy over a constant KB, which is known as Boltzmann's constant, times the temperature. Okay? Again, it's an exponential dependence on energy and temperature. Okay. Anyway, so they said, yes, we're going to apply the same distribution to these oscillators, right? Because Boltzmann was successful in getting the ideal gas law. Okay, so we have all possible frequencies, but we're going to use this distribution that some energies are more likely than other energies. Okay? All right, so they did that. Lots of math. And what happened? Well, they get a spectrum, right? And when they plot it, I'm going to go back to the summary notes. No, I'm not. I'm going to go back to that PowerPoint plot. It's easier to see. Here's what they get. Oh, this looks pretty good. It looks pretty good for long wavelengths. This is their derived results, known as the Rayleigh-Jeans law. This curve, this predicted curve. I'm calling it here classical theory, the old theory. But you can see what happens. This is at 5,000 K. As you go down in wavelength, their intensity goes off towards infinity. And there's a cool name for this, the fact that they didn't get this agreement. Historically now, this is known as the ultraviolet catastrophe. That their predicted curve deviates strongly from the observed spectrum curve as you go to shorter and shorter wavelengths into the ultraviolet. Okay, so something didn't work. Well, guess what? Guy comes along named Max Planck. There he is right there. All right, and what Planck does is he says, hey, I'm going to use the same distribution, the Boltzmann distribution, but I'm going to tweak it so that I can actually get one of these curves. So at 5,000 Kelvin, for instance, I know what I should get based on experiment. So let me see what I can do. Well, what he does is something very strange, and he admits that it's very strange. What he does is he assumes that if you look at one of these oscillators right here, see, when Rayleigh and Jeans did this, they said, this oscillator can have any energy at this frequency because it depends on the amplitude of the oscillation, right? The amplitude of that oscillation. The bigger the amplitude, the more energy is associated with that oscillator. In fact, if you even think of a mass on a spring, it's analogous to that. The bigger the amplitude, even though the natural frequency of the oscillation is the same, the bigger the amplitude, the more energy, kinetic energy with that oscillator. So the same thing here. So Rayleigh and Jeans, they said, well, at a particular frequency f, this oscillator can have any energy. It's in the language of distributions, this is a continuous energy distribution, okay? But what Planck did to get things to work is he said, no, at frequency f, the oscillator this charge that's moving back and forth can only have certain energies. So in the language of probability distributions, what he did is he made this a discrete energy distribution. So right here, this E at a particular frequency, instead of it being any energy, Planck said, nope, can only have certain energies. Now again, he knew what he had to get, so this helped him figure out how to define the energy. And what he ended up saying was the energy of an oscillator, right, can only be some integer, and we use n. So I know it's not the best choice. This ain't index anymore in this part. Times a constant that we write now as h times the frequency. Okay, so n here is equal to an integer, 1, 2, 3. H is now known as Planck's constant. And he got a value that is very close to more carefully determined values, and it's 6.63 times 10 to the minus 34, and the SI units here are joule times seconds. You'll see this in the summary notes. All right, so I'm going to wrap this up because I've been talking too long. But what Planck was, and we'll pick up this idea in the next video, is he said an oscillator can only have certain energies. Oh, I'm going to throw out the term quantized right now. So this is sometimes known as quantizing the energy. So the energy is quantized because it can only have certain values. Okay? And it turns out he was able to get the actual spectrum. He actually derived a function, and if you plot that function at a certain temperature, you'll get one of those spectra. It's amazing, the shape. Okay? All right, so this is the advent of quantum optics. Now, we'll say more about this in the next video. But what you should know from this video is you should know this Rayleigh-Jeans ultraviolet catastrophe, what we mean by that. In particular, you should know what the shapes, like just, what a typical shape of the actual spectrum looks like, what the Rayleigh-Jeans result looks like, which is it just goes like this. That's the ultraviolet catastrophe. And you should also know these formulas right here in the summary notes. These are valid formulas. In fact, once Planck was able to get the spectrum predicted, he also was able to derive from theory Wiens Displacement Law, because all you have to do now is maximize the function, and he was able to get a function, an expression. Okay, and he also is able to theoretically derive Stefan's law, because that's related to the area underneath the curve. Really cool. Okay, all right, we'll pick up the consequences of this in the next video. Bye-bye.